This video demonstrates how to obtain the inverse Laplace transform of a stable LTI system from its HAS. In this question, the Laplace domain transfer function of a stable LTI system is given, and we are asked to find the impulse response of the system, HAT. To do this, we first need to review a few points. The first point is that the Laplace transform of e to the power of minus at ut is equal to 1 divided by s plus a, with the ROC real S greater than minus a. The second point is that the Laplace transform of minus e to the power of minus at u minus t is also equal to 1 divided by s plus a, but with the region of convergence real S less than minus a. The third point is that the Laplace transform of te to the power of minus at ut is equal to 1 divided by s plus a squared, with the ROC real S greater than minus a. The fourth point is that the Laplace transform of minus te to the power of minus at u minus t is also equal to 1 divided by s plus a squared, but with the ROC real S less than minus a. And the fifth point is that if an LTI system is stable, its region of convergence must include the j omega axis. In other words, in the S-plane, the j omega axis must lie inside the region of convergence. Now let's solve the question. First, we decompose HS into simpler fractions. In this transfer function, the degree of the denominator is higher than the degree of the numerator. Also, we have a repeated root and a total of 3 roots in the denominator. Therefore, the partial fraction expansion will have 3 terms. One with denominator s plus 1, one with denominator s plus 1 squared, and one with denominator s plus 2. Now we need to determine the numerator of these fractions, which we call a, b, and c. To find a, we first multiply hs by s plus 1 squared and take the derivative, and finally substitute the remaining s values with the root of the denominator, which is s equal to minus 1. When we do this, the s plus 1 squared terms in the numerator and denominator cancel out, and we are left with taking the derivative of s plus 3 divided by s plus 2. This derivative is obtained by taking the derivative of the numerator times the denominator minus the derivative of the denominator times the numerator, all divided by the denominator squared. Now, if we substitute s equal to minus 1, the value of a becomes minus 1. To find b, we don't take a derivative. We simply multiply hs by s plus 1 squared and then substitute s equal to minus 1 for the remaining s values. Doing this gives us s plus 3 divided by s plus 2, and by substituting s equal to minus 1, we obtain be equal to 2. To find c, we multiply hs by s plus 2 and then substitute s equal to minus 2, which is the root of that denominator. Doing this gives us s plus 3 divided by s plus 1 squared, and by substituting s equal to minus 2, the result becomes 1. These relationships for a, b, and c are general rules that can be used for similar fractions where there is a repeated root in the denominator. Now we take the inverse Laplace transform of the simplified hs to obtain ht. The first fraction is similar to the Laplace transform cases in points 1 and 2, so a is equal to 1. The second fraction is similar to the Laplace transform cases in points 3 and 4, so again a is equal to 1. The third fraction is similar to points 1 and 2, so a is equal to 2. For the first fraction, as mentioned, is corresponds to points 1 and 2. Therefore, with the coefficient minus 1, if really s is greater than minus 1, the inverse Laplace transform is minus e to the power of minus t ut. If real s is less than minus 1, the inverse Laplace transform becomes e to the power of minus t u minus t. The second fraction corresponds to points 3 and 4. Therefore, with the coefficient 2, if real s is greater than minus 1, the inverse Laplace transform is two t e to the power of minus t ut. If real s is less than minus 1, the inverse Laplace transform becomes 2 times minus t e to the power of minus t u minus t. Finally, the first fraction also corresponds to points 1 and 2. So, depending on whether the real s is greater than minus 2 or less than minus 2, its inverse Laplace transform is obtained accordingly. Now, to obtain ht, we must choose the correct inverse Laplace transforms. For this selection, we use the fifth points. We must choose the inverse Laplace transforms whose region of convergence include the j omega axis because the system is stated to be stable. From the first two options, the case with real s greater than minus 1 included the j omega axis. So we choose minus e to the power of minus t ut. From the second pair, again, the case with real s greater than minus 1 included the j omega axis. So we choose 2t e to the power of minus t ut. And from the first pair, the case with real s greater than minus 2 included the j omega axis. So we choose e to the power of minus 2t ut. In this way, the impulse response ht is fully obtained. In this video, we solved a sample problem from the topic of the Laplace transform. If this video was useful for you, you can follow our other videos on the channel as well.